Hopefully by now you've finished questions 4 and 5. So in this last video, I just want to make some general comments about the conclusions you can draw from question number 5 and how to make sure that you put into context the importance of a recursive versus an explicit equation. Generally speaking, hopefully you found that the explicit equation is the most useful for problems like number 5, letter A. The 95th term involves a lot of iterative steps to take a sequence that you're given, which in this case stops with the 4th term, and requires you to do all of those extra subtractions. In this case, it's subtracting 5. So subtracting 5, 5, 5, 5, 5, 5, 5, 5, all the way down to the 95th terms just sounds almost impossible. Like, even if I could do all of those subtractions, just the sheer amount of time it would take is a little bit mind-blowing. So the explicit equation comes in real handy for things like this, because to find the 95th term, what you could very easily do is plug n equals 95 into the explicit equation and simply evaluate the explicit equation by doing that little bit of algebra. Usually the explicit equation is a basic algebra equation to do, so if you did number 5, letter A, and just quickly plugged in 95 into your explicit equation, which you would have had on the previous page, then that would have given you the 95th term. Now, of course, if you didn't necessarily, you can quickly check, but this is the other way that the explicit equation can come in handy. It's with a graphing calculator. If I know the explicit equation was 14 minus 5n, if I remember correctly. Now remember, when you type it into a calculator, it'll say 5x, but no big deal. And then, just to quickly check my table, nope, need to reset it. There we go. I know that these were the terms that they were giving me. First term is 9, second term is 4, third term is -1, fourth term is -6. So I know it's good. And I can use the table jump feature, second table set, start at the 95th term. And then, of course, I can easily find that the 95th term is -461 in my table. But either way, I needed the explicit equation to type into my calculator in the first place. So whether you use it for actual algebra by hand or whether you use it for calculator work, the explicit equation is the one that very, very quickly can give us the 95th term. And that efficiency is why the explicit equation is still so valuable. On the other hand, if you take a look at letter B, it said to find the 5th term in the sequence, which equation would be more valuable. Some people may argue that plugging in 5 into the explicit equation and simply doing that math isn't hard. So some people may have said, well, the explicit equation is always the most valuable, I'll use that for everything, which is fine. But it is worth noting here that the original sequence gave us the first term, which is n equals 1, the second term, the third term, the fourth term, and the 5th term is simply one more past the last one they gave me. If they gave me the 4th, the 5th term was the very next one. And if I think about the pattern, subtract 5, subtract 5, subtract 5, I could very quickly simply subtract 5 and get that the 5th term is -11. Now, of course, I could do the fancy table thing. I could go to the 5th term. I can check that it's -11. Or, as I said, I could take the 5 and plug it into my explicit equation and solve the explicit equation to get -11 as an answer. But the whole point of a recursive definition is to simply tell us very quickly how to get to the next term. And the recursive definition already told us subtract 5. That explicit business almost seems like more work than it's really needed. So that's the thing that I want you to kind of think about, generally speaking. When would explicit versus when would recursive be more useful an approach? In my opinion, and this is not official mathematical opinion, this is just me kind of opining from experience alone, I've kind of found that those two types of equations, recursive and explicit, are useful in the following ways. Recursive is useful in a short-term context. So I'm going back to my scratch work from the previous page. This was the problem in question number 3. But I just want to point out the recursive definition was fine when I had the 10th term, wanted to find the 9th. Or if I found the 9th term and wanted to find the 8th. If I was thinking very short term, to just find the terms that are kind of close to the one that I was given, the recursive definition is really quite easy to use. Most people are probably at the point now where they could look at a recursive definition like this one and simply say to themselves, oh, to get to this term, take the previous one minus 5. And they could translate it in their head. They could realize, oh, minus 5. That's the pattern. Boom, done. The recursive definition might communicate very clearly, and in short-term problems where you don't have to go very far in the table, I think the recursive definition is great because it can save you a lot of time and tedious work. You don't need a calculator, you don't need any fancy algebra, you don't need any tools. On the other hand, the explicit equation was great for problems that really had big jumps in the table. Like to jump all the way to the 85th term in that problem was impossible to do efficiently with a table alone or with a recursive definition alone. So I needed the explicit equation in order to either help me solve algebraically or help me use my calculator. So that in context is why I do want you to kind of think about those two possible situations, short term versus long term. Recursive equations are generally more useful in what I refer to as short-term problems, which is where you're trying to find terms that are relatively close to the one you're given. If you're given the 10th, the recursive definition helps you find everything very quickly in the neighborhood of the 10th term. But if you have to go pretty far beyond, like if they gave you the 10th term but they want the 85th term, that's where the explicit equation comes in more handy. Making long-term jumps in the table is usually best suited to the explicit equation. So I will ask that if you haven't already, you put something like that in your own words in number 5, letter C, but try to generalize that for yourself. When would recursive be useful? When would explicit be useful? Because no problem is really ever going to say use the explicit or use the recursive. It's just going to ask you to find the value of the term, and it's up to you to know which equation would be more valuable for that purpose. Now, to complete the rest of the questions on this page, I am going to ask you to exercise that judgment, because you'll notice things like in question number 6, letter C, it asks you which equation would be more helpful here and why. This is where you're really articulating that same type of thinking again. If you need to find the perimeter or find the figure that has a perimeter of 76, which equation would kind of help you there? Is 76 in the neighborhood of some of the things you've already found? Because if so, the recursive definition might be a good choice. Is 76 pretty far away from what you already have going on from the given information? Because if so, the explicit may be more useful in that situation. So as you're working through this question, it's going to ask you to write a recursive and an explicit so that you're equipped with both sets of tools, and then in letter C to exercise that judgment. One quick thing to note about question number 6, it's a question about perimeter. So it's not asking you in this question how many little squares are in each figure. It's asking you what the perimeter of each shape is going to be. So just as kind of a quick heads up, and I'm going to just set up a quick little organization table for you to think about this. The pattern that they're referring to here in each shape is contingent on the shape number. Shape number 1 would kind of be like the first shape, so n is 1. But the T of n, the pattern itself, is to count the perimeter. So if I start from this corner, I have a perimeter of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So T of n must be 10. And if you thought, oh, wait, that's not what I was thinking about, just kind of keep that in mind. You do have to count the number of squares that go around the outer edge of the shape in order to generate the first few terms in the sequence. So the second term in the sequence would be figure 2, and that would be a perimeter of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then, of course, the pattern will continue. Now, hopefully, by the time you do the third one, or the fourth one, you're going to notice a pattern. because it's going to get really tedious to keep drawing all those little square figures, and that's certainly not the point of this question, is to just completely wear you down with tedium. So look for patterns, and once you see a pattern, you can kind of abandon the counting individually thing, and you can simply use your pattern to help you not only finish as much of the table as you need, but to write your recursive definition. Notice the box for this is a little bit bigger because a true recursive definition has two things. You need to be able to write one specific term in the sequence that kind of it serves as a starter term, and the actual recursive equation itself. So just remembering that structure. And you'll be given enough information to write the explicit equation as well. Once you get those two equations, again, you'll have a judgment call to make in letter C. Which equation would be most helpful to answer that problem? After you finish that problem, questions numbers 7 and 8 are more examples of somewhat unorthodox recursive definitions. Remember on the previous page, question number 3 was kind of an unorthodox recursive definition. It started you at the 10th term and gave you information to find the 9th. Kind of strange. These are more examples of that sort of strangeness. In number 7, the notation is a little bit strange. They are giving you a sub 0 equals 1, a sub 1 equals 2. That's the same as saying that the 0 term is 1 and the first term is 2 in that T of n notation. So just notice that flexibility here. A sub is the same as T of. So a sub 0 is T of 0, or simply code for the 0 term. If you translate this information into a table, then you don't really have to worry too much about the notation. This is telling you that the 0 term is 1, the first term is 2, and to get to the next term, so a sub n, or T of n, you'll have 2 times a sub, or T of n minus 1, minus T of n minus 2 plus 1. Now that one is really unorthodox. We've never seen one like that before. If you explored the Fibonacci sequence in the previous series of videos, you may have kind of seen one that looks like this, which is great, but it's unorthodox looking. And the whole point of this is to really just kind of challenge yourself, to ask yourself, how can we best understand this? How can we use the substitution and the algebra instincts that we have to help us understand what this recursive definition is trying to get us to do? Now, if you look at the learning plan for the week, you'll have noticed that all I've asked you to complete is this page, and I didn't specifically ask you to complete the page after. This is page 8, but I just want to point out, if you want to do more stuff with recursive problems, this page will not be required, but may be worth trying just for fun, or, dare I use the word fun here, for enrichment, simply so you can see more examples of recursive problems. None of these would be required. None of these would have come up on an assessment or a homework assignment or anything like that. They're just extension problems, problems for you to explore, especially if you feel like this sort of interests you, or this is something that you actually have time that you want to kind of dig a little bit deeper into. The answer key for this page is posted, but again, it's not required, so feel free to challenge yourself with some problems, or maybe just one problem, and if time is limited for you and you just don't feel like you have the ability to focus on them, then don't worry, you can skip page 8 altogether. In any case, once this video is done, take some time to finish all of question number 8 and above, and make sure that the ideas make sense. If you need to take some time to record some long-term notes, that would probably be a good thing as well, so that you can really make sure that the big ideas, the main idea behind recursive versus explicit equations, is clear before you move to the next lesson. The next lesson is a pretty big departure. We're going to start something completely new in the next lesson, so that's why this is a very important formative moment for your thinking, so you can make sure that you really have a solid grasp of recursive, because from this point forward, we're probably going to see those questions creep into Big Ideas Math assignments. You'll see them creep into quick checks, and we'll start to review them more throughout the chapter as they pop up in different contexts.